I'm in the biochemistry, a brief course book again. I'm on page 120. It says here, effect of temperature on enzyme activity. I don't know if you can read that. It says here, figure 412 illustrates the time course of an enzymatic reaction conducted at various temperatures. An attempt to determine the optimal temperature for this reaction would yield 3 different values for each of the 3 time periods designated T1, T2, and T3. Although the initial reaction velocity appears to increase with an increase in temperature up to 80 Celsius, more careful examination of these curves shows that above 50 degrees there is a falling off in activity with time, the decrease being more marked at a higher temperature. Meaning, when you rise the temperature of where the enzyme is and how effective it is, its effectiveness drops off. You see how it drops off on those curves right there? And the colder it is, it stays steady all the way up. These results are due to 2 factors. An increased initial velocity because of the increased temperature, meaning the enzymes are moving around a lot faster, they're jiggling around, so obviously there's going to be a lot more activity because it's warmer. As well, and inactivation of the enzyme at higher temperatures due to denaturation, meaning the enzyme falls apart. And I wrote a little notes here. When you look up enzymes, and I suggest my viewers do that, you have, your native, secondary, tertiary, and or quaternary structure of the proteins or nucleic acids. And when those structures are lost, or when they're partially lost, they result in a loss of bioactivity, meaning they're not effective anymore because they're broken apart. They don't work anymore. And this has everything to do with cell evolution, and when the star starts forming enzymes from all the molecules combining together. Meaning, the strongest, most stable enzymes or catalytic type material will begin the processes that life requires for it to start evolving, to start combining all the molecules, to start repeating little processes over and over and over again. And one of those materials is the same material inside of catalytic converters inside of vehicles. It's platinum. I think platinum plays a role in the initial catalyzing of some material to start off the bioactivity of other types of chemicals as well. I'm pretty sure if you can make the connection there, I think there's somewhere in that avenue, but I really can't do that right now because it would take a whole hell of a lot of time. But I just want to let my readers and my audience think about that for a second. Platinum wouldn't denaturize. It wouldn't fall apart. You can crush platinum to very, 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 very high pressures and temperatures, and it's still platinum. It's not going to fall apart like a biological molecule would. And it also would remain the catalytic. It would still remain a great catalyzer for a lot of reactions. So, because a lot of the proteins, they would fall apart because of elevated temperatures, elevated pressures, or the introduction of salt or organic solvents, or with other chemicals, or with radiation or heat. Biology is very, very delicate. So in order to begin the process of life, you would have to have some enzyme or enzymatic type material that can sustain those really high pressures and heats that are inside of the evolving star, more or less along the lines of late-stage red dwarfs in their interiors and inside of early brown dwarfs and even late-stage brown dwarfs. But then once those materials start combining together, such as, carboxylic acid, which is COOH, they combine with, other radicals such as methylene and other types of radicals in H2N to form the amino acid called leucine, which is alpha amino isocoperic acid. And I just went ahead and wrote that out here. I don't know if you can see it, but Yeah, basically you have to form those specific radicals first. You know, the CH3, CH3, the CH, CH2, H2N connected to CH, and then COOH on the top end. And that also tells me a lot about where this molecule is synthesized as well. You know, they say stars have a lot of hydrogen and carbon, and you know, well, there it is. Look at this molecule. The damn amino acid has a whole bunch of hydrogen in it. That's where the hydrogen goes. It goes to forming biological molecules. And as well, it also tells me that it happens near the surface of a star as the surface starts cooling down. So I would guess it would say, I'm probably thinking that the process is similar to photosynthesis and other types of other reactions where the biology, the biosphere starts out really in the high atmosphere of Neptune and Uranus, you know, and Jupiter and Saturn, and then it kind of moves down as the atmosphere starts dissipating and all those elements are combining with each other, forming amino acids, and then it starts raining down onto the interior, and then, you know, it has a lot of water in there, a lot of different types of organic material that mixes. So basically that's one thing I want people to keep in mind, that it's not that life forms on a star as it is right now, because it's way too hot. What happens is as that star cools and the material starts cooling down, it combines and forms ionic and covalent bonds with other elements, and then those bonds start forming, and then boom, you have the formation of these amino acids, and then those amino acids get facilitated by other chemicals that were already there, that were also being formed as those other amino acids were formed. So they have the lock and key type thing going on there. I read that in there. I'm not going to go over this talk though, but basically that's it. I would want to definitely study enzymes and the role that pressure and heat has in their formation and their denaturation as well. You know, go to the library and find books like this. Find like these old school books that have all this, you know, high quality information in there. I mean, it's one thing to go on the internet, but it's another thing entirely to go to the library or bookstore and just find these old school books. I mean, look at these diagrams. This is really good stuff. Okay, you can read it on your own. You don't even have to go to a college course and pay thousands of dollars. You can teach yourself this stuff at your home or sitting in your car. Today is October 5th, 2015. Hopefully people can take these thoughts and use them. All right, later.